Okay. All right, now it's recording. Okay. So with energy flow in ecosystems, we talked the other day about photosynthesis. All right, so the plants, and you will have to memorize the formula for photosynthesis. Take a look at my screen here, guys. All right, you see it? All right, so the plant's going to take in 6 carbon dioxide. That's the stuff we breathe out, and you will have to memorize the formula. Okay, 6 carbon dioxide. It brings in 6 waters from the roots. Okay, adds it to the solar energy. And none of this is going to happen unless chlorophyll is present. Like I said, we can't do this. We talked about that the other day. When they do their photosynthesis, they are going to produce a single glucose molecule. Okay, C6H12O6. You do have to memorize the formula for glucose. And in the process, they're also going to release oxygen extra. All right, so we talked about how you could count up the actual molecules. The easiest example to remind you is right here at the beginning. Do you see my mouse? Can you see where my mouse is wiggling down there? All right, 6 carbons right here in 6 carbon dioxide. There's 6 carbons right here in glucose. Okay, then if you count up the hydrogen next, we're looking for 12 hydrogens to make this glucose molecule. And right here they are, 6 H2s. That's 12 hydrogens. All right. And now we need 6 oxygens to make the glucose molecule, but we have way extras. All right, so take a look at our oxygens. Right here at the beginning in carbon dioxide, there's 12 of them just right here. So you have the 6 at the beginning and the 2 at the end. So you have 12 oxygens right here in the carbon dioxide, and we only need 6 of them. So stack up the extras to just get rid of. Okay, so we only need 6. So right here we got 12. And then over here, we have another 6. So there's 18 oxygens altogether. We only need 6 of them. So we're going to dump 12 of them out into the atmosphere. Right here they are, 6 O2s. So we're going to dump out 12 of them because they were extra and we don't need them. All right, and that's why plants release oxygen so that we can breathe it in. Okay, so that's how photosynthesis works. And when they're making their glucose molecule, they store the extras as starches. Glucose are tiny little molecules, tiny little molecules, and storing a whole bunch of them. That's what the plants use for energy. Storing a whole bunch of them is very difficult. So what they do, instead of storing a whole bunch of little bitty molecules, they stack them up. Okay, just like if the little bitty glucose molecules are pennies, you don't want to carry a bunch of pennies around. So you're going to carry a $20 bill or a $50 bill, or maybe if you're lucky, a $100 bill, depending on that. And so plants do the same sort of thing. Glucose molecules are very, very tiny. You don't want to store a whole bunch of tiny molecules, so they stack them up together in sugars and starches. That's why sugars, starches, and sugars. Okay, starches, sugars. Okay, announcements. Okay, all right, so they store the extra sugars they make as starches, and they're called carbohydrates. Okay, sugars and starches are called carbohydrates, and that's how they store them. So when plants are doing photosynthesis, we call them producers. Okay, because they can take something that you can't hold in a bucket like sunshine. They can take inorganic molecules and turn it into organic molecules. And because they do that, we call them autotrophs. Auto means self, and troph comes from the word for feeding barnyard animals, a trough. Autotroph means self-feeder. That's what we call the producers. Consumers, anything that has to eat, is called a heterotroph, means eats from the outside. Okay, that's what we are and all the other animals. All right, so when a rabbit eats another plant, the energy is what's transferred. The energy from the clover it eats gets transferred up to the rabbit. And then when the coyote eats that, the energy goes. All right, so the energy is transferred up as things are eaten. Technically, it's the energy from the sunlight. Okay, the energy from the sunlight is what the plants took. They took energy from the sunlight and turned it physical into glucose. So the plants get their energy directly from the sunlight, and then the consumers get it indirectly after that. The we always say that everything comes from the sun, but we talked the other day that there's an exception to that rule. At the bottom of the ocean, there are bacteria. They don't need sunlight. At the bottom of the ocean, there is no sunlight. So how can you have food webs at the bottom of the ocean where there is no photosynthesis possible? Okay, there's underwater vents, underwater volcanoes, and hydrothermal vents that release chemicals. There are bacteria that can eat that chemical. Usually the chemical is hydrogen sulfide. And so the bacteria can take that inorganic molecule, hydrogen sulfide, and turn it into their version of sugar. It's not glucose, but it's a different type of sugar. It's still a sugar. So when the bacteria take the hydrogen sulfide that's coming out of the volcanic vents, they turn that into their sugar. Then something can eat the bacteria, and then something eats that, and something eats that, and something eats that. And that's how you get energy in the bottom of the ocean with no sun. So they're getting their energy from these chemicals, not from light. So you can't call it photosynthesis. Photo means light. You can't call it photosynthesis. There's no light. They're using chemicals, so you call it chemosynthesis. Okay, but that's the only exception of the rule. Everybody else is getting their energy from the sun. All right, so then we have our types of consumers. 4 types of consumers, basically. Herbivores eat plants, carnivores eat animals, omnivores eat both, and decomposers eat dead organic matter. But they don't just eat the dead stuff, they return the nutrients to the soil. We talked about this the other day, and most of you guys are pretty good with those. Now, but here's where it gets a little tricky. Does everybody listen for the tricky part? Okay, when we're talking about food chains, okay, down at the bottom of the food chains, at the beginning of every food chain, you have a producer of some sort. Usually it's a plant, or underwater it might be one of these bacteria, but it's a producer. That's at the bottom of the food chain. And then an herbivore is going to eat that. Remember, herbivores eat plants. So the next step up on the food chain is going to be an herbivore. Herbivores are the first one to eat anything, so we call them primary consumers. Okay, you got producers at the bottom. Those are our plants, or that chemosynthetic bacteria. At the bottom, you have our producers. And then the herbivores are right there eating those plants, sometimes omnivores because they eat plants too. Those are our primary consumers, the first one to eat anything. Now, whatever eats this primary consumer is called a secondary consumer. When the coyote eats the rabbit, okay, that's a secondary consumer. And then say a wolf kills and eats the coyote, that's tertiary. Tertiary means 3. Tertiary. Okay, that's our tertiary consumer. And then if, let's see, that was a wolf. Let's say a mountain lion eats the wolf. Okay, that would be quaternary. You hear the word quarter in there? Quaternary consumer. So you count the consumers going up. It always starts with a producer, always starts with a producer. And then you've got the primary consumer, secondary consumer, tertiary consumer, and if it's a very healthy ecosystem, you can have a quaternary, sometimes even a quintenary, sometimes. You don't put the decomposers in the pyramid because they can show up anywhere, okay? All right, so now, once you've got this energy moving up through the pyramid, they've gotten the food, they've eaten their food, they have the energy in their bodies, and the plants have the energy that they just made from the sun. Once you have the energy in the organism, how do you use it? That's where we start the new stuff. Okay, once you have the energy in the body, whether it's the plants with the photosynthesis, they got the, because the plants need the energy too, right? They didn't do that. They didn't do photosynthesis just for us so they could grow carrots and potatoes and lettuce leaves. They didn't do that just for us. They did it for themselves. So once plants make the glucose, they have to use it also. So what do we do? How do we break down the glucose? This is what we're talking about, cellular respiration. This is a new formula for us. There's 2 formulas, okay? And they work kind of opposite of each other. It's really neat. So cellular respiration, that's the second. That's once you've got the energy, how do you use it? All right, so cellular respiration is a process by which we get the energy out of our carbohydrates. Remember, that's our sugars and starches. So we get the energy from our carbohydrates. You take in oxygen from the atmosphere, mix it with the glucose that you've got in your food. Take the oxygen you're breathing in. That's why you breathe in. So that you can have that oxygen. You mix it with the glucose you eat. All right. You do your chemical equation on it. You break it down. So what you're doing, you've got the glucose in the food you eat or the glucose that the plant's made, and you break it down. You breathe in your oxygen, and basically you're like burning it. Do you guys know that when you have a candle won't burn without oxygen? Wave at me, guys. Y'all listening? Whoever can hear me, wave. Good, good. Can you hear me? Thank you, Martel. Anybody else can hear me? Wave at me if you can hear me. Thank you, Kashawn. I see you, Jakaya. Thank you. Iverson, can you hear me, man? Kayla's not even in her camera. Good? All right, so here's what I'm trying to say. Have you ever, do you know for a fact that you can't burn a candle without oxygen, right? When you are digesting your food, you need to breathe an oxygen so that you can digest your food. It's almost like burning a candle. You're burning, you've heard it said burning fuel, right? When your food is your fuel. Put the two together. The reason we breathe in is so that you can break down your food. And so once you break down your glucose, all right, then you're ready to, you have to add the oxygen. Here's the formula to make it happen. And again, I told you you'll have to memorize this formula too. Here's the glucose we just brought in, and we bring in 6 oxygens. Do you recall that the plant put off 6 oxygen? Think with me, guys, because you got a lot of you guys haven't had much chemistry yet. Do you recall that the plant put off 6 oxygen? Well, here the 6 oxygen, that's what we breathe in. We have to breathe in the exact same amount. So you have the glucose molecule, you have to bring in 6 oxygen to break it apart. When you do the chemical reaction, okay, you're back out to the 6 carbon dioxide, exactly the same number that the plant took in. You're putting out 6 water molecules. That's why we can fog up a mirror. It's water vapor. It's not, I'm not talking spit dripping off your face. I'm not talking spit. I'm talking water vapor. Okay, this is why we can fog a mirror. All right, so we put off 6 carbon dioxide and we put off 6 water vapors, exactly what the plant brought in. And we get energy out of it. The energy is called ATP. Okay, right now you just need to know that it's energy. I'm not going to call it ATP on the test, but you will need that for biology. The chemical energy that we get out of glucose, we eat the glucose, we do our chemical reaction on it, and the energy we get out is called ATP, adenosine triphosphate, but the letters are easier. ATP, and that's the energy that we use to run our bodies with. If you need to walk up a flight of stairs, if you need to move from your couch to your kitchen, if you need to just breathe, all of that requires energy. If you're having a dream, the energy in your head, that's energy. Okay, that energy that we use to run our bodies is called ATP, and that's what we get when we digest our food right here during photosynthesis. So please be aware, you're going to need to memorize this formula. Okay, we have testing on campus. So you guys know this. It's a little crazy. All right, so the part of the energy that it's obtained, we use that to carry out our daily activities. When we walk and breathe and read a book, okay, we also use it to grow our bodies. If you have a cut or a scratch, okay, I don't know if any of you guys are skateboarders or whatever. We used to have skateboarders all the time. There aren't as many, but say you're a skateboarder and you crash and you've got a big scar on your elbow or your knee. All right, you're going to need to heal yourself. Your body will heal itself. It needs this energy to do so. So it's not just, or if you have a cold, when your body needs to fight off a cold, your body needs the energy to do so. That's just what we do. It's not just for running up the stairs. It's for everything. And when you take in more energy than you need at any one time, the extra is stored as sugars or fats. All right. And so all living things do this cellular respiration. Like I said, the plants didn't make the carrots and potatoes for us. They made it for themselves. So yes, the consumers are going to break down glucose. The consumers are going to break down glucose to get the energy out of it, but plants are as well. So the plants do both formulas. Plants do photosynthesis to make the energy, but they also do cellular respiration to use the energy. Consumers only do cellular respiration. Okay, they have to eat something and then do cellular respiration on it. So plants do both formulas. All right, so every time one organism eats another, you have this energy transfer going up the pyramid. And one of the easiest ways to study food webs and food chains is this is a food chain. Like I said, you know this. Okay, it's a single stack. This one is an ocean food chain where you have this algae down here, this photosynthesis. Now there's 2 kinds of algae or plankton. Okay, you have phytoplankton, phyto for the word for light again, phytoplankton, they can do photosynthesis, and then you have zooplankton. Those are little consumers. Do you hear the word zoo, like animal, zoo? Okay, phytoplankton is like a plant. It does photosynthesis. Zooplankton is like an animal. It's a consumer. So the phytoplankton is the beginning of the food chains in the ocean. Okay, the algae that can do photosynthesis. And then something small like a krill will eat that. And then you go on up all the way up the food chain. All right, now that is a food chain right there. Now this next one is a food web. Of course, you know this, okay, because you're not always going to have the exact same thing for lunch. And within an ecosystem, you have to have more choices. And so that's the food web. And again, most of you guys know this. It shows all the different feeding relations that are possible in that ecosystem. But what we also call them when you go up the chains, this is something you may not have heard before. They're called trophic levels. He's missed almost the whole lesson. 744. All righty. All right. So what you may not have heard before is that when you have these steps on the food chain, they're called trophic levels. There's that word again. This is the third time I've used that a type of that word. You know, I said trough, like when you feed the animals. I said autotrophs. Autotrophs, that was the other word for producers, right? Autotrophs is the other word for producer. And then I said heterotroph, okay, which that's the other word for consumer. Hetero means from the outside or different than. So heterotrophs, it has to eat something from the outside. And then now I'm saying trophic levels, and they're called feeding levels. So the word troph, or the suffix troph, means to eat or to feed. So trophic levels, okay, this is what we were talking about when you have the producers down at the bottom, okay, and then you have the herbivores that eat the plants, or an omnivore, because they can eat plants too. That's called the primary consumer. That's so the producer is the first trophic level. Then the primary consumers, okay, that's the next trophic level. And then secondary consumers, tertiary consumers, quaternary consumers. Those are the different trophic levels, feeding levels. And at each level, you're going to get a different amount of energy. This is the whole thing, is how we get this energy. All right. Now, at the different levels, different amounts of energy is going to go up the pyramid. All right. Because some of the heat is going to get lost every time. Think about a food chain where you have grass and a cricket and a bird. Or we could do like Mosamac. Let's use Mosamac food chain. So grass, cricket, frog, fox. Okay. So there's a whole bunch of energy in the grass because the grass was doing photosynthesis. And then the cricket eats the grass. All right. But if you have, like, say, the space of my computer is how much grass that cricket would eat in a week. All right. He's going to use most of that energy that he gets from the grass jumping around and chirping, having cricket girlfriends, or running and jumping and playing and chirping. He's going to use almost all of that energy to jump around and live. When the frog eats the cricket, only 10% of the energy he got from his grass that he ate in the week, only 10% of that energy actually turned into cricket meat. So the frog only gets 10% of what the cricket got. Think about that, because it's called the rule of 10, or the law of 10. Okay, so try to focus with me what I'm saying. If the cricket eats this much grass in a week, but he spends most of the energy he got from the grass just jumping around. When the frog eats him, he only gets 10%. And then the frog is going to use that energy croaking and swimming and jumping and doing the stuff frog needs to do. And so when the fox eats him, he only gets 10% because the frog was only turned 10% of his energy into meat. So the fox only gets 10%. So it's called the rule of 10. And so as you go up each step of the pyramid, you can knock off, you know how when you're doing math, okay, if you got tens, all you do is add a zero or take away a zero to the whatever number you got, right? So let's say at the bottom level, it's like rule of tens. Let's do something easy, say 500. Okay, 500 kilocalories. Okay, it's way more than that, but we can start with something easy, 500. So let's say the grass. Is everybody focused? This is some numbers and some math. Is everybody good? We're learning the rule of 10, and that is new. I'm pretty sure most of you guys don't know it. You know what food chains are, and you know what herbivores and carnivores are, but you probably don't know the rule of 10. Are you listening? Okay, so let's use these numbers. Let's say there's 500 kilocalories of energy in this much grass. 500. All right, so when the cricket is eating that, okay, He's getting that 500 kilocalories of energy, but he only turns 10% into meat. So 500 now turns to 50. So you just knock off a zero because it's tens, right? 500 just turned to 50. All right. And so he only turned 50 kilocalories of that into actually cricket meat. So when the frog eats him, he only gets 50 calories. Now, the frog is he's going to have to eat a whole bunch of them, but the frog is going to take the 50 calories that he got from this one grasshopper and he's going to jump around and move. And therefore, he's only going to turn 5 kilocalories into frog meat. Only 5 of that's going to get to turn into muscles. So when the fox eats him, he only gets 5. So from 500 to 50 to 5. Each time you go up, only 10% of the energy goes up to the next level. That's why the top levels are small. That's why they use a pyramid, because you have so much less energy. Only 10% of the energy goes up each level. They call it the rule of 10. All right. The rest of that energy gets lost as heat into the atmosphere or used up during daily activities. So the other 90% is lost and only 10% goes up the ladder. That's also why you have a lot fewer predators on top than you do the prey animals beneath there, because so little energy gets transferred up. And so that's why that the lions are going to the zebras are going to outnumber the lions about 1,000 to 1. Okay, so it takes about 1,000 zebras to feed one lion. Sort of. It's not exactly that same, but that's how there's that many more zebras per lion. So because of that, the number of trophic levels on the pyramid rarely gets above 4. Like I said, sometimes you can get quaternary, that's the 5th level up top. Remember, we start primary, secondary, tertiary, quaternary, and sometimes quaternary. Okay, so that's why the levels are so much smaller at top. If there is anything that can survive at quaternary level, something that can live off of a lion, it's something small like a flea. Okay, so the big animals, you can't get much higher than that. Usually 4th level, quaternary, is maximum for most food chains. Sometimes you can get to quaternary level, but by then, so much of the energy is lost that there's not enough to feed a big animal that high up. Usually anything that high is going to be something tiny. All right, so here's the main ideas of our lessons right here. So the majority of the Earth's organisms depend on the sun for energy, with that exception of down in the bottom of the ocean. The producers are going to harness the sun's energy directly through photosynthesis. And then while the consumers use the sun's energy indirectly by eating the producers or other consumers. So the plants get it directly and consumers get it indirectly. So the paths of energy transfer can be followed using food chains, which is a single path, food webs, which is multiple paths, and trophic levels, which is what we show in the pyramids. Only about 10% of the energy that any organism consumes is going to be stored as meat and transferred up to the next level. Only 10% gets transferred up. All right, and I think that might be, yeah, that is the end of our notes for today. Do you guys understand? I went through it pretty quick to make sure I could do the whole thing. Do you guys think you have it all? Do you guys have any questions for me? All right, so I'm gonna stop the video here in just a few minutes, but what I need you to do is I need you to check again over our due dates. Let me repeat them one more time just to make sure you got them. Your notes and key terms, the notes for this section and your key terms and objectives, the last day to turn that in is the 6th if you haven't done it. And MOSAMAC, the last day to turn that in is the 7th. Both of those are in Power School right now, so you can check. The current work, the crash course, links in the chain video, and what's for dinner worksheet. Both of those were due last night. Today's a 90. 90's not too bad if it's not in yet, but both of those should be in. The crash course and what's for dinner should both be in. They were due last night. The food web packet I gave you yesterday is due tomorrow. So with that food web packet, I put your instructions on there, but just in case, it's a coloring sheet. If you can figure out how to color it on your computer, then you can have bonus points. The coloring's not required. What I need you to do is do that reading and answer the questions. Do not Google your answers. Do not make up answers that you think sound good. Every one of those questions is word for word in the reading. Please put the right answer in there. That's what I'll be looking for. Don't make something up. It's all right there in the reading. Okay, that's the part that's required. Food chains, food webs, and then pyramids. Those three, it's a packet. That's why I gave you extra time to do it. You had all day yesterday. You'll have today, and then I'm going to give you tomorrow. It's due tomorrow. And again, tomorrow is another asynchronous day, so you can work on it all day tomorrow. All right, so do you have any questions for me? Okay, I'm going to pause the video. Let's see.